Arratsaldeon. Hace no sé cuántos años, pero en septiembre de 1973 yo llegaba a Cambridge, al Cavendish Laboratory de la Universidad de Cambridge, donde se ha descubierto el electrón, el neutrón, la estructura doble hélice del ADN. Y en la vida de unas personas hay momentos de suerte. Y ahí yo tuve un gran momento de suerte, que me encontré con John Pendry, ahora Sir John, fue mi director de tesis y no he dejado de apreciarle y admirarle desde entonces. Sir John Pendry es físico teórico. Después de estar en Cambridge se traslada, ahora trabaja en el Blackett Laboratory del Imperial College de London. Después del Cavendish dirigió el grupo de teoría del laboratorio Desbury y, en colaboración con la empresa Marconi, ha diseñado una serie de metamateriales que son materiales artificiales, novedosos, con propiedades que no se encuentran en la naturaleza. Sir John Pendry ha sido el jefe del Departamento de Física del Imperial College y también decano de la Facultad de Ciencias Físicas. Tiene numerosas distinciones, entre las que señalaría es Fellow de la Royal Society, Premio Dirac, es medalla de la Royal Society y en 2004 fue distinguido por sus honores o por sus servicios a la ciencia en honor de Sir. Hay que decir que le cogió trabajando en San Sebastián y lo celebramos muy bien porque él sabe disfrutar de otros placeres de la vida, además de la ciencia, relacionados con la charla de ayer, la primera. John combina en un brillante e inusual manera profundidad física con virtuosidad matemática. Su trabajo en electromagnetismo le muestra en la cima de su creatividad. Ha contribuido a muchos campos de la física, cambia de tema cada 10 años. Cualquiera de estos campos, sus contribuciones le bastarían para justificar una carrera. Pero es en este último campo donde ha tenido el privilegio que pocos científicos pueden tener, que es abrir un campo totalmente nuevo, ¿no? Y en realidad lo admirable de este trabajo es que estaba allí. Estaba en las ecuaciones de Maxwell, al que Croto se refería ayer como uno de los grandes hitos de la historia de la ciencia. Hay una frase, creo que es de Boltzmann, ¿es acaso un dios el que ha escrito estas ecuaciones? Pues John ve en las ecuaciones de Maxwell lo que todos teníamos delante y no lo habíamos visto. Lo mismo que hizo Einstein con la teoría de la relatividad restringida, ¿no? Su trabajo, un trabajo clásico, es su trabajo sobre lentes perfectas e índices de refracción negativo. Recuerdo a John diciéndole a su mujer, Lady Pat, que es con nosotros, este trabajo no sé si lo voy a publicar, no me atrevo. Si lo publico, o una de dos, o me convierto en alguien muy famoso o adquiero la total infamidad. Pues famoso es él, ha abierto nuevos campos, está en línea, ha cambiado la perspectiva de mucha gente y hoy cientos de personas trabajan en estos campos. Hace un año yo tuve el privilegio de ser invitado por el Imperial College y por el Instituto de Ciencias Física Británico para dar el discurso después de la cena en el homenaje que le hicieron a John Pendry, lo cual ya indica el apetito por riesgo de John Pendry, conociendo mi acento roncalés en la lengua inglesa. En cualquier caso, también es el chairman del Scientific Committee de nanoGUNE, del Comité Científico de nanoGUNE, que incidentalmente se reúne mañana. Pitar que nos dirá pronto a qué hora, y contestó de una forma generosa, rápida, y ha colaborado en todo lo que le hemos pedido de una forma eficiente, dedicada y ejemplar. Es un privilegio ser su amigo y tenerle aquí con nosotros. Sir John.
Well, thank you, Pedro, for that introduction. It's an honour and a pleasure to be here in San Sebastian giving this lecture. It's a town I've visited many times, and each time has been very enjoyable. I want to tell you about some new ideas which we're very excited about in optics. And these ideas go under the name of transformation optics because they're very different from some of the ideas which have gone in the past. So the old optics was about treating light as a collection of rays. It was about refraction at discrete interfaces. So if you wanted to design a camera lens, it was all about the shape of the surface of the glass. And this was because you had at your disposal very limited material properties. The number of materials which you think you might find in nature is very, very large, but the number of properties you actually find in nature is very small relative to what you might want to achieve things in optics. So in this new vision, we go beyond the ray approximation, and this is very important for nanotechnology, which is what this conference is about, because light has a problem with nanotechnology. You can't see anything smaller than the wavelength of light. The wavelength of light is the order of 500 nanometers, and in the talks that we've been hearing today and yesterday and the day before, we're talking about structures which are tens of nanometers across. You can't see them with light. So to have light interact with these structures and to be useful in investigating these structures, we have to go beyond the conventional optics, which can only control on this very gross scale. So when you send electrons through one of Intel's computer chips, they travel on these 35 nanometer wires. When you send photons across the Atlantic as part of the internet traffic, they travel in an optical fiber which is many microns across. It's about 100 to 1,000 times thicker than the wire of the electron. And it's partly to address these problems that we're having to develop the new optics. And the key is in what's called the near field. When you shine light on an object such as your hand, and then you try to magnify that object, there is this limitation of the wavelength of light. But that's only a limitation when you come to try to form an image. If you went in with a scanning probe, a very fine needle, and you investigated the structure in the light at your hand, then there is actually structure in the electric and the magnetic fields right down to the level of the atom. So there are things to be seen there. It's just that the information that we're trying to see remains locked into the surface. So the far field escapes from the surface, but it only contains this limited detail of what's there. And the near field, which is still staying at the surface, is containing all the very fine detail of information. And it's partly to control the information in this near field that transformation optics is being developed. So it's about near field optics, which is really sub-wavelength optics. And it's all very well talking about what you want to do. You might even have a theory of how you might do it. But when it comes to making a practical realization, you have to find some materials out of which you can make your optical instrument. And I've mentioned already that nature has been rather parsimonious in allocating optical materials to us. And so we have to answer this with extending this spectrum of materials, and this new sort of material, a metamaterial, which I'll come back to, is the way we do that. So that's the agenda. And I'd just like to remind you that optics is a very old subject. And so you might ask, if people have been working on it for so long, how can it be that there are still things to be discovered? But I hope to show you that there are. So we're going to be talking about refraction, of course, and that's very old. Snell is credited with the invention of Snell's law, which we call it in English-speaking countries. It was also invented at the same time by Descartes, so if you go to a French school, it will be called Descartes' law. But anyway, it's the same law. Also, very important is the use of lenses to make images. The word lens comes from lentil, which I have a picture of it here. It's not a very good picture, but this is a little bean which is used in cookery in the Far East and in the Middle East, and also, well, we use it here as well. And you can see that it's shaped like a lens, the lens, same shape that we use for focusing light. And this man is Galileo. He didn't invent the lens. Lenses have been around for much longer than Galileo has been around. And what he did was to actually make a lens much more perfect than had been made before. And with the lenses he used, he was able to see the moons of Jupiter, which he named after his patrons, the Medici. So we're going to be talking about focusing light. And, of course, this man gets in every story, doesn't he? I don't need to tell you who he is. And he had something to say about light as well. He considered the problem of what happens when you have a very strongly gravitational object, such as the sun, or in extremis, a black hole, a very massive object. And he developed his theory of general relativity. And one of the predictions of that theory was that a massive object can not only attract heavy things like the Earth or the Moon, but it can also attract light. And that was a very, very radical proposition, because at that time people believed that light propagated through empty space, and space was empty, and therefore it was nothing, and therefore to change the properties of nothing was to talk nonsense. But that's what Einstein said that a gravitational object should do. And it was this prediction of the deviation of light by a massive object that actually propelled Einstein to fame. In 1919, Arthur Stanley Eddington mounted 2 expeditions to test Einstein's theory. And what he wanted to test was whether the sun deviates starlight, which passes close by. Now, you normally can't see stars when they're close to the sun, because you look up and what you see is a very bright blue sky, and the stars are completely hidden. But you can see them when there's an eclipse. And when there's an eclipse, the stars then become visible, and you can watch them vanish behind the sun. And in 1919, there's an eclipse which was visible, which was total on the equator. And he set up his 2 experiments, and he measured the angular position of the star, and then somewhat later, when the sun had moved away and when it was night, he again measured the position of the star, and he found a difference. It was a very, very small difference, but it was measurable, and it confirmed Einstein's theory. That was the first scientific paper and the last scientific paper that appeared on the front page of the London Times. And it rocketed Einstein from merely being a very famous and gifted scientist to being the icon of 20th century science that we know today. So we're going to steal a bit of Einstein's theory because this deviation of light by the sun gives us a clue to how we might control light in a much more flexible way than a lens does. A lens deviates light at its surface, but you can also make a continuous deviation of the light. And the way Einstein described this deviation was to say that a heavy object like the sun distorts space. It squashes it or stretches it. And the extent to which it does this was described by a quantity g, which is the metric, simply the measure of the space. And when Einstein rewrote Maxwell's equations in the way that his theory required, he discovered that this quantity, the metric, how much you squash space, looks exactly like the refractive index, the power of the material to bend things. So when you bend space, when you squash space, it's like creating a little lens, and that's why the sun deviates light, because it's acting like a lens. And Einstein had a formula which related this stretching of space to the refractive index. And what's more, we discovered that if you imagine a ray of light going through ordinary space, so imagine space as a sort of rubber sheet, and I'm going to draw on this rubber sheet some lines, and here's a ray of light, and I don't want the ray of light to go there, I want it to go there. And so if I stretch space, then it turns out that as you stretch space, you actually take the path of the ray of light with you. So it's as if this light was nailed to this rubber sheet, which we're imagining to be space. And when you've done stretching and pulling, the ray of light is going in the direction you want. And then, please, Mr. Einstein, how much have I stretched the space? What is the refractive index I need? And so we're going to use this technology inherited from Einstein to calculate what refractive index we need to control the light. And this can be thought of in mathematical terms as a coordinate transformation, and hence the name transformation optics. So we'd had this idea, which we thought was very nice, and we had to find a way of telling it to people. And you're a scientific audience, so you appreciate Einstein. Some of you are perhaps mathematical and know about coordinate transformations. I'm not sure many people would be very pleased if I presented the expression for the refractive index in terms of the first derivatives of the coordinate transformations. So what we had to do was to think of a way of expressing our excitement to the community that this was a very powerful tool. And so after scratching our heads for some time, we came up with the idea that we could actually use this technology to hide something completely, and so completely that you don't even know there's something hidden. We can make something invisible. And so we set that as our task. And let me explain why it's really hard to make something invisible. This is a picture of Peter Pan. And if you just make Peter black, then you can still see that he's there. You can't see him because he's not reflecting any light, but you know he's there because you can't see what's behind him. He's got a shadow, and that's why I've chosen Peter Pan. Actually, there are two reasons I've chosen Peter Pan. The first is that in the story of Peter Pan, he's the little boy who loses his shadow. But the other reason is that his statue is in Kensington Gardens near my college, so something of a college icon. So what you've got to do is not only stop Peter from reflecting any light, you've also got to take away his shadow, and then he will be invisible. So how do we do that? Well, actually, it is very simple to describe, at any rate. So what I've drawn here are some rays of light coming in from somewhere, and perhaps you're looking at these rays of light in order to see some trees or what have you here. And I want to hide this brown object here. And the first thing I must do is to deviate the rays of light so that they never strike that object. And so I wrap a cloak around this object, and I deviate the rays of light, but I mustn't throw them away, because if I do, there'll be a shadow. And I've got to put them back on the same trajectory that they were traveling originally. So it's as if these rays of light have gone in a straight line. And if they're still going in this straight line when they come out of the cloak, you won't know there's a cloak there, because your eye has no awareness that the light has done this deviation around the hidden object. But how do we create an object like that? Well, you imagine that you start with light going in straight lines, and then you imagine that you have this rubber sheet, and you tear the rubber sheet, and you make a hole in it, and here's the hole you've made, and the rest of the rubber sheet you squash into this region here. And if you remember what I said in the earlier slide, when you move the rubber sheet, the rays of light are nailed to it, so they too are all expelled from this region here. But if you don't distort the rubber sheet in this region, they're not changed at all. So only in this region does the rubber sheet stretch. Only in this region do you need to change the refractive index. And you have a formula for that through transformation optics. Thank you, Mr. Einstein. Actually, there are examples in nature of light being continuously deviated like this. And one example is the mirage. So how does a mirage work? Well, traditionally they occur in the desert when you have very hot conditions, and the sand is heated by the sunlight and is much hotter than the air above. But the air immediately in contact with the sand will also be quite hot, and that will be less dense and therefore less refracting than the cool air above. So you actually have a gradient in density, and that in turn will create a gradient in the refracting powers of the air. So when light comes down here, it sees this gradient of the refractive index, and it's continuously bent until it's refracted into your eye. And of course, if you see some sky reflected like that, you scratch your head and think, well, what does reflect sky? It's water, yes? So the thirsty traveler is cruelly deceived that there's water there. There isn't. There's just hot air. In Europe, we more commonly see these road mirages where the tarmac gets very hot and the road in the distance looks as though it's wet. And this is the best I can do. This is from the web, but you can see a reflection of the car in what appears to be water. It isn't water, it's just a hot road. And this is a trick we are going to do. We're going to have a gradient in the refractive index, and we're going to create the mirage of invisibility by continuously varying the refractive index of a medium, so that when we're done, we're going to have something like this in David Shuring's illustration of our cloak. So in comes the light. It goes around here. Okay. So how are we going to achieve that? Because although I've just said with a wave of the hand that we're going to vary the refractive index, that is not a simple thing to do. And you often don't have the materials available with which to do that. And so we're going to have to make use of this new concept in materials that I've mentioned already, metamaterials. So what are metamaterials? An ordinary material, the way it refracts light has to do with its chemical composition. So the electric field present in the light polarizes the atoms or molecules, and it's the way they respond that determines how the light is refracted. And there are many billions of molecules in a cubic wavelength, so it's really the average response. It's not the way they individually respond, it's just the average. Now, the things that respond don't have to be as small as an atom or molecule. Typically, an atom or molecule is less than a nanometer across. The wavelength of light is just a bit less than a micron, so it's 1,000 times bigger. And you can actually have structures which are several tens of nanometers across, and they'd still behave just as though they were rather large molecules. And that's the idea of a metamaterial. And in fact, if you're not dealing with light, if you're dealing with radar waves, where the wavelength is 10 centimeters, then to be less than the wavelength of a radar wave, you need only be a few millimeters across. So many of these ideas have been tried out for radar waves, not for light waves. But I think you can see that if you add to the design flexibility to choose a chemical composition, the design flexibility to choose the shape of these entities, of these holes or structures which you build in, then the possibilities are almost endless. So you have a very, very rich array of properties in metamaterials. You can quite easily design a metamaterial that can make a cloak. You can even make a metamaterial that has properties that are not found in nature, such as a negative refractive index, and I'll come to that later in my talk. So we're going to use these metamaterials to make a cloak. And the first cloak was made by my friend and collaborator David Smith in Duke University in 2006. But it wasn't a cloak for visible light. It was a cloak for radar waves. Simply because these structures are easier to build at radar frequencies. But, of course, everybody is more excited by light than they are by radar waves, unless you happen to be in the Air Force or somewhere. And so the race was on to make a cloak that worked for light. And to make a cloak that works at optical frequencies, you have to make a metamaterial which has the structure much smaller, which is nanometric. So that's why the nanotechnology comes in. And a very smart postdoc of mine, Jensen Lee, actually produced a design. Details don't matter too much, but he produced a design for making a cloak out of silicon resting on a reflecting metal surface. And that was a theoretical paper, but it gave a target for the nanotechnologists to build a cloak. And one of the things he did, which was quite clever, was to so here are those coordinates I drew before, and you remember that to make the cloak we tear a hole in this rubber sheet and compress the coordinates in one direction, and that's what I've done here. I've made a little tunnel on this reflecting surface, and I'm going to hide something in here so that you can't tell I've hidden something. But I've actually done a very simple coordinate transformation. I've just pushed all these little cubes up here. And in doing so, I've done something which is rather unfortunate. I've made them anisotropic. And if you look at these, you can see that they started off as squares, but they aren't square anymore. They're little parallelograms. And that actually is difficult to make, and it means that the cloak won't be perfect. So instead, you can do a much more clever transformation in which you arrange that these little squares stay squares, they only change the area. And this was one of the clever things that my postdoc Jensen Lee achieved. And then it was actually possible for the people in Berkeley to make this. But first I'll show you some computer simulations. Here is our little tunnel in which we're hiding things. It's actually got a metal upper surface to it, okay? And so when you shine light on it, if you shine light on a flat surface, you just get one beam coming off. If you shine light on this structure here, it's actually got two little mirrors, so you see two beams coming off, and that's the signature that there's something there. So if you were just shining a laser beam like this on this surface, it would suddenly flick into two beams, and you say, aha, somebody's hiding there. I know that. However, if you wrap this cloak around it, which we designed, then you can shine this light on here, and it's deviated in such a way that you only get one beam back, exactly as if this surface was perfectly flat. So that was a challenge to the experimentalists. And earlier this year, the Berkeley group of Professor Jiang Zhang, actually Jensen had decamped them because he wanted to do some experiments, so he now reappears in Berkeley. And they were able to build this cloak. And it operates actually not in visible light. This is the light which is used for telecommunications on optical fibers, which carries the internet. So it's a very important frequency band, and so it's very important to control light here. So let me show you a picture of that cloak. First of all, this is a graphical representation of what they were trying to do. So this is a two-dimensional system, and the light is trapped in this layer of silicon here. And here is the cloak. Sorry, here is the cloak. And the way they altered the refractive index of the cloak was very simple. They just drilled holes in it. The simplest metamaterial you can imagine. And by altering the density of holes, so they were able to alter the refractive index of the cloak according to this prescription which we designed in London. And then you have this hidden area here which no light can penetrate into, and therefore you can't see inside here. But what's more, when the light comes into this cloak, it behaves exactly as if this region were flat and not curved into a little tunnel. There's an electron micrograph somewhere, I think, that, yeah. So here's an electron microscope picture. This is 1 micron here. And you can see that in their fab, they've drilled holes in the silicon to reduce the refractive index. And there's this cloaking region here where you can see the density of the holes changing. And then what they did was to shine light on the cloak. So here's some flat silicon, and you shine light on flat silicon, and what you see is a single reflective beam. So they then shine light on the uncloaked bump, and what you see is actually 3 beams here, but you can definitely tell there's something there that isn't smooth. And then they wrap the cloak around their tunnel, and once more you see 1 beam again. So a very simple demonstration. It's the first one at optical frequencies. There was a similar experiment done at Cornell. So people are now beginning to control light at optical frequencies in a completely new way. They don't design interfaces. What they do is to make a 2- or 3-dimensional variation of the refractive index, as I showed you on the last slide. So this is a continuous variation of the refractive index, and with that they were able to build the cloak. Now, one thing I want to... So this was a demonstration of how powerful transformation optics is, how useful metamaterials are, and it certainly created a lot of interest, and many thousands of people are working in this area trying to improve things. But it's not the only thing that transformation optics and metamaterials can do. It's a general tool for controlling light. And in particular, metamaterials have a trick that was known to be theoretically possible, but was never realized in practice until recently. And the guy who thought about this was called Veselago, and he looked at the experiment which Snell would have recognized, in which light is refracted by, in this case, an ordinary material such as glass or water, and the light is deflected towards the normal. Now, Veselago said, what happens if you have a medium where the light doesn't come out this side of the normal, but comes out this side of the normal? And you may think, big deal, positive angle, negative angle. Why does it matter? Why is this man getting so excited about this negative angle. Well, I'd remind you of where we came in. We were talking about Einstein, and Einstein related the compression of space to the refractive index. So if you take a piece of space and you compress it, it becomes more refracting. However, so you can have a correspondence between a refractive index and a piece of squashed space. But now you're in a dilemma. Of course, this man, Veselago, has said you can have something with a negative refractive index. How are you going to think about a piece of space which hasn't just been squashed, it's been made negative? It's anti-space. It's a piece of space that destroys another piece of space put next to it. It's the ultimate terminator. Fortunately, it's only light that sees space in this way, not human beings. But let me show you some of the things that negative refraction can do. So Veselago knew that you could actually focus light with this negative refracting effect. And he didn't think of light in terms of negative refraction in terms of negative space, but later we've come to realize through transformation optics that what this piece of negative refraction here is doing is actually annihilating the space next to it. So the light comes back to where it was here. And it also, this bit, annihilates the next bit of space. So it's like destroying the intervening space so that a point here comes to an image here. Another way of representing it is that as far as the light is concerned, it's going forwards, backwards, and forwards. And so it passes this point 3 times, once here, once here, once here, hence the 3 foci, because you've done this folding operation of space. You've tucked it back inside itself, if you can imagine that sort of strange manifold happening. So this is a totally new way of focusing light. There are no curved surfaces here, and yet the light is focused. And it was this strange aspect of the light that led me some years ago to think, this lens that Veselago proposes, I know it focuses light. We have other means of focusing light. We have lenses, so, but it's doing it in a different way. Is there something special about this lens? And I was led to think of this because as far as Maxwell's equation is concerned, this point is this point here. The effect of the space in between totally vanishes. And so I take you back to another point that I made at the beginning of my lecture, which had to do with resolution of a lens and the fact that it was limited because there were 2 sorts of light. There was the light that escaped from the surface and you could use, but gave you an image limited by the wavelength. And there was the near field, the light which stayed trapped near the surface and which you couldn't capture with an ordinary lens. But this trapped light, this near field, has all this high-resolution information contained within it. And so here's the question. If this space is truly removed and the fields here are truly the same as they are there, surely both the near and the far fields should be present here, and this lens should be perfect. It should focus everything, providing you can make it perfectly. And I thought, well, that's nonsense, because this limit of wavelength resolution is been embedded in optics for a long time. And I did the calculations of Maxwell's equations, and my conclusions were that the image is perfect, providing that you make the lens according to this prescription here. So eventually I published that, and there was a hell of a row with the referees, but eventually it got through, and it's now accepted that it's very difficult to make a lens like this, but I'll show you some attempts at it towards the end of my talk. But if you can, then indeed this conclusion of perfect focusing is true. And this is enormously useful because it now brings the control of light onto the nanoscale. And the way negative refraction is achieved is by using properties which we've heard about in the nano conference, which has been going on in the mornings. And those are plasmons. And they are now recognized as having the capability of helping us, just like this lens does, helping us control light, not on the scale of the wavelength, but on the scale of nanometers. And therefore, the nano world can now make use of light on a much finer scale and make much more use of it. But in the last section of my talk, I want to just play with transformation optics and show you how, using the concept of transformation optics and a little bit of imagination, you can have a lot of fun with optical devices. So let's take this lens, which Vesilago designed, and say, well, I don't want a flat lens. I don't want an image the same size as the object. I want a magnified image. Okay, let's put down this rubber sheet, and if the image isn't the right size, we're going to stretch it a bit. So I pull and stretch, and what I'm going to do is to turn this flat slab of material, I'm going to turn it into a spherical annulus, and as a result, the image will stretch, and the object will, of course, stay the same size. It will look like this. So by applying a transformation, I can pull this negative bit round in a circle here, and what I've made is a magnifying glass. And the function of this magnifying glass is to take everything which is in this green inner sphere here, which I've colored red, the shell is green, and it appears to an outside observer as though it fills this region here. So I made a spherical magnifying glass. And that's quite strange because I use this analogy of, I should bring a milk bottle with me because it works better with milk. But have you ever noticed that if you look at a fluid in a glass or a glass bottle, the fluid actually goes right to the edge of the glass? You can't see the thickness of the glass. And that's easily explained with refraction because every ray of light that strikes the glass actually goes into the fluid. So if it's milk, you see the white going right to the edge of the bottle. But what have we here? If this is milk and you're an outside observer, that's the edge of the bottle, remember. This is free space out here. Then the milk appears out here. It's a sort of super milk bottle that magnifies what's in here, and it makes it appear as though it's much bigger than any physical object here. Just try and work out how it might do that. It's a really, really puzzling thing. Well, let's solve Maxwell's equations and see if it really does that. And here we have some ray tracing which takes light, which hits this negative refraction here and is compressed into this inner region here. So every ray that hits this red circle is captured inside the green circle. And the theory says you should capture even these rays here at the top and put them in here. But of course, these rays don't strike anything. They don't strike the milk bottle. And so how are these put in here? I'll leave you to work that out. But here's a picture of not just a ray diagram, but of Maxwell's equations, which shows the waves entering this red thing being compressed in here. And actually, I don't do many movies, but I do have a little movie of this happening, and that might be fun to show. Let's see if it works. If you have epilepsy, don't look at this. No, it's not funny. Don't look at it if you have epilepsy. And so you can see the waves coming in from the left. And one property of this negative refracting material is that the waves go in one direction and the energy in the other. So the energy is always flowing from left to right. But when the energy of the wave enters the negative refracting material, the waves are actually heading in an opposite direction. And that enables it to act like I call it an optical turbine, and you can see that the wavefronts are compressed into a much shorter wavelength in this inner region here. Okay, people who are made ill by that can now look up. And I won't explain it here, but I'll just ask you to think about how these rays do get in here, because what Maxwell's equations show that they do. Now, how can we exploit that? Well, suppose you want to do the following. Suppose that you want to make a really big umbrella. Well, let's make it more scientific. Suppose you have a satellite and you want to shield that satellite from the sun, okay? But you don't want a huge piece of metal here. You want to make a shadow that's really big, but you want to make the shadow with a small object. Well, let me go back to this figure here, and if I put an umbrella in here and I arrange the parameters outside, then what light will see is not a small umbrella, but it will be magnified and it will be a huge umbrella here. So this device can take any small object like an umbrella and it can make it seem very, very large. So what happens when we do that? Well, my student, Wei-Sheng Wei, has done some calculations, and what he has is something which is very black inside this inner region. He's got some negative refracting material here, and this is all empty space. And you can see that if the design parameters are precisely right, he can create this enormous shadow here, which is actually much bigger than in fact, the object which is creating the shadow is actually smaller than the wavelength. So that's quite remarkable. The effect tends to go away if you've got some loss, but nevertheless, that's something you can do. What else can you do? Well, there are things called retroreflectors. These are usually two mirrors at right angles like this. And if you have that sort of mirror situation, light comes in, bounces off this mirror, it bounces off the second mirror, and it goes back exactly in the direction it came from. And they use these things, for example, there are retroreflectors on the moon, and they used to measure the distance between the Earth and the moon very accurately, because if you shine a laser on the moon, even a much more powerful laser than this, you can't see the little spot it makes. But if you shine it at a retroreflector, actually enough energy comes back that you can see the reflection from the moon and do measurements with it. So, but the retroreflector has to be much bigger than the wavelength. So we can handle that. So what we do is to put a very, very tiny retroreflector in here. Now you've got my lens in here, and you have a tiny retroreflector, which is much less than the wavelength, and light comes in, and here's the computer simulation of the retroreflector from this very small device providing reflection. Now, finally, I want to show you how experiments can now show how you can use the Veselago lens to resolve much better than the wavelength. This is a huge challenge, as I've indicated. The computer chips, the amount of data written on your DVD is limited by the quality of lenses, and if you could solve this resolution problem, there'd be lots of things you can do. And the first step to it has been taken by the Zhang group in Berkeley, and what they did was to make an approximation to this lens. The approximation, strangely enough, is a slab of pure silver. I can explain why later if you like. So what they're trying to do here is to take objects which are all much less than the wavelength. They're all a few tens of nanometers across. So this is a chromium layer, and there's a grating, there's the word nano. And then there's 40 nanometers of spacer layer, which is polymethyl methacrylate, and then the silver lens. And the image is too small to be seen, but it's actually written a photoresist and measured by a scanning force microscope. The wavelength of illumination is 365 nanometers. And the trick is to get the silver incredibly flat, which is very, very hard. And here are their data, and what they showed was that you can resolve things much less than the wavelength. A grating of the order of 1/6 of the wavelength can be resolved, but to the eye, it's much more impressive to look at this word, nano. So there's the nano that was written in the chromium image with an ion beam system. And here's what you see if there's no lens. So it gets blurred, and if you do a scan across these letters, you see they're as wide as the wavelength, approximately. But if you now pop on your silver spectacles, and the image sharpens up and is now as sharp as the 1/6 of the wavelength. So that brings me to the end of my lecture. What I hope I've shown you is that optics is now going through a period where there are some very exciting ideas, surprisingly new ideas in what was known as classical optics, which is now undergoing a little bit of a revolution on account of this, and that not only are these ideas exciting theoretically, but because of this concept of metamaterials, many of them can actually be implemented and have been implemented. And so we're looking forward to some very exciting developments and making an optical contribution to nanotechnology. And with that, I thank you for your attention.
Okay, there's time for one or two questions, please. Una o dos preguntas, por favor. No? Henry? Of course, please.
So, did I understand right? You have normal light, and then you do some manipulation in the near field domain, and afterwards you transform it again to normal light. I mean, when we want to see it, we cannot see it in the near field regime.
We can't see it, but what could see it would be a semiconductor detector, for example. So if you wanted to do, here are the things you could do with this lens. First of all, you could write much smaller dots on DVD. And that would enable you, instead of, what does a Blu-ray disc have, 60 gigabytes, you could maybe increase it to a terabyte, and so save Jose even more money than he has already with a magnetic disc. Because the magnetic discs now have much more data than the DVD. What else could you do? Well, we talk about light on a chip. You could do that at the moment, but the chip would have to be 100 times bigger than an electronic chip, a big, heavy thing. If you really wanted to make light on a chip useful, you'd have to get it down to the nanoscale, and then you'd have to control it on that scale, and that's where these ideas of near-field transformation optics come in. There is a way of making that light visible. What you do is put all these sub-wavelength optics things inside one of these spherical super lenses, and then they're magnified until they're big, and then you can see them, providing you made them bigger than the wavelength.
But you need some type of device who makes these very small structures.
Yes.
Okay. What would this be?
At radar waves, if you're working with radar waves, where most of the demonstrators have taken place, this isn't a problem. You typically etch them on circuit boards and then assemble the circuit boards into little metallic structures, which you use as lenses or whatever. So it's just ordinary engineering at radar waves. For optical metamaterials, you have to use nanotechnology, which means something like either electrolytic etching or ion beam, focused ion beam technology. At the moment, that's very expensive, and also there's a limit to what you can do. So everything's much harder at the optical range of the spectrum, but we're getting there.
Okay, I think about the millipede. You see, Wesley, okay.
Oh, yeah, yes.
So let me follow up with that question. How small do you really need them? How small do the structures have to be? You say that they have to be very small in order to work with optics.
Typically a tenth of the wavelength.
A tenth of a wavelength?
Yes. That's not so small.
But we can do that.
You can do that. Indeed, you can, yes.
Yeah.
But here's the trick. You have to do it in 3 dimensions, not 2.
Well...
And I know you're working on it too, because you told us, yes?
We'll leave it at that.
So, I didn't understand the physics of this umbrella you mentioned.
Oh, yeah.
So, you have an atom with light, and you excite the atom has a shadow, like a lambda, of the other lambda.
Yes.
So the cross-section is lambda squared.
Yeah.
Is similar to the effect you mentioned, or what's the difference between these two phenomena?
Well, from the way you describe things, I think you have quite a strong scientific background, yes? So can I talk about... You can get scatters of light which are quite small, but have very huge physical cross-sections to scattering light, even though their physical cross-section is small. And typically, this happens when the tiny structure traps light for a time before it releases it. It's a resonance, in other words. Now, if you just have an ordinary resonance in a molecule or something, you can get a very large scattering cross-section, but it doesn't make this sharp shadow. It just scatters the light everywhere instead of in a controlled way. And what we're doing is making, essentially, what this device does is to make a collection of resonances which are very finely tuned so that they add up to make the sharp shadow with a cross-section much larger than the physical object. So it's resonances again. Sorry to the rest of you, not sure what resonances are. But
there's one last question. Aichol?
Hello. So lately I've seen some more, exotic proposals, like the cover of Nature Physics last month, about something like black holes for light, employing this kind of transformation optics. Can you tell some words about this? I don't understand what.
Yes, I think that particular illustration was stretching things a little bit, and there are some analogies with black holes, and there's some things this negative refraction can do which are similar to what happens in black holes, but generally speaking, the key thing about a black hole is that it emits radiation, and it does this because there's a source of energy, which is the gravitational field. Now, if you have a passive optical material, even if it's got a negative refractive index, there's no source of power in there, so it can't really look like a black hole. So I think they were pulling your leg with the cover, to be honest.
Thank you very much, John, for this fantastic lecture. I'll go to the funeral. I'll see you in the dinner.